Okay, so thank you for coming. I hope that the talk is worth your time. This is about data removal, and I'm going to tell you what this problem is. And this is based on a joint work with my PhD student, Hao Lin. And Arnab, who was a PhD student at Columbia, did a postdoc at UPenn, and then ended up being a faculty member at Ohio State. And Kamyar, who was a PhD student at Columbia, I guess 12, 13 years ago, and he's now at City University of New York. And most of the credit of the work goes to Howlin and Arnab, who did most of the heavy lifting in the project. Okay, so let me start with a standard model that we have for supervised learning problems. We have a data set that has n data points. Okay, so we have this is our data set. It has n data points, and it has a bunch of features. Each data point has a bunch of features that are represented with vector xi, and then we are using the features to make a prediction about response yi. And kind of a standard assumption in supervised learning is that these things have are IID independent and have the same distribution. But I have made one extra assumption about the joint distribution. So the conditional distribution of yi given xi is a function of xi transpose beta star, very similar to generalized linear models. And xi is coming from a distribution p that we don't know. This, for example, as I mentioned, is very standard in generalized linear models. At the end of the talk, I'm going to mention one of the papers that shows how this can be extended to neural networks without going to the details of that paper. So one point that I want to emphasize here is that the feature vectors are p-dimensional. So we have p features, and we have n data points. And when we talk about high dimensionality, I'm going to clarify it later, but we assume that p and n are both large. So it's not that n is 10 billion and p is like 10. Both of them could be extremely large. So that's one of the assumptions we have throughout the talk, that p and n are very large. And in this talk, I'm going to focus mainly on the situation that p and n are at the same order. So, but again, I'm going to clarify the assumptions more later. Whatever our downstream task is, the first thing that we usually do is to estimate beta hat or beta star. We want to get an estimate of beta star in that model. And we usually use, for example, this optimization problem, which we call it regularized empirical risk minimization. So let's say this component is the negative likelihood that we are including here. And then we add regularizer to somehow control the variance of the estimator, especially given that we are in high dimensional settings. So this is our estimator, and there are so many classical examples from lasso to logistic, linear, Poisson regression, collaborative filtering, and we can mention many other examples that are using this model. So this is the model, but what is the data removal problem? So let's say we have our estimator, we have solved this optimization problem, usually an expensive optimization problem, and we get beta hat. And for some reasons that I'm going to clarify later, we are asked to remove either one data point or a few of the data points from the data set. So there are many reasons why we would like to do that. And I'm going to mention in the next slide, but let's say we are asked to remove a bunch of elements, but for the simplicity in this talk, I'm going to focus on one data point, removing one data point, but the results can be extended to more than one data point. So we are asked to remove this one. And not only we have to remove it from the data set, but we want to remove the trace of this data point from our estimate. So in other words, I would like to calculate beta hat minus k, which is the minimization when the kth data point is removed from our optimization problem as well. So we can just retrain the model, essentially solve the optimization problem again with an iterative algorithm, and get beta hat minus k, but this is not efficient. Especially as you will see in the applications, we want to do this process over and over. So it's not that I'm going to just remove one data point and this is done. Again, the next day, I'm going to be asked to remove a bunch of other data points. So I have, or add a few other data points. So this process has to be repeated over and over. And for that reason, we don't want to solve this optimization problem again. We just want to find an efficient algorithm to probably approximate, not even solving it exactly, approximate this one. And we want this efficient algorithm to be also accurate. And when I talk about accuracy, I want to evaluate the accuracy in high dimensions, where the number of features P, the number of features in Xi, is comparable to the ambient dimension or the number of data points N. Okay, so before I explain the problem more, let me tell you some of the applications of this problem. Some of them are more recent applications, and some of them are, oh, there is a, I don't see them. I guess I have to go through. And let me see. I guess I have to expand this.
So it's not about. Oh, is a slide stuck on the first page?
Okay, let me.
Oh, interesting. Maybe start.
Should we? Okay, so we're here.
Yeah, why was it not showing? I'm not sure.
So, can you see slide 4 now?
Yes,
Okay.
we can see.
Maybe I'll do it like this. So I just.
Yeah, maybe just make this big.
Okay, I'm gonna make it big. Makes sense. Let me.
Sorry about that.
Okay, let me just ask if they are. Okay. Okay. So, there are some of these applications are more recent one, and some of them are classical ones. The classical applications are like outlier detection, that we use this technique for it, or hyperparameter tuning. I'm going to mention a little bit more about hyperparameter tuning later, but there's a bunch of other applications that are new. For example, one of the applications that I'm going to mention a bit more towards the end of the talk is machine learning. So let's say Google has this large model, and this large model, for example, the large language model, has been trained based on many users' data points, and then you can prompt the model and get the outcome from, let's say, Gemini, right? But then because of the privacy laws, especially in Europe and California, if a user asks Google to remove their data from the data set, Google is supposed to remove that data from the data set, but also the trace of that data point from the models that they have, right? So as you can imagine, this is a very expensive process if they want to retrain the model. And of course, these requests, they receive some bunch of these requests every day. Even if they can wait for a week, every week, more or less, they have to update their models to make sure that they are preserving the privacy of the users who ask their data to be removed. So this is called machine learning. So we want to remove the trace of the data point of a user from their ML model. And they, again, want to make sure that this is quite efficient. It's not retraining the entire model. Then there are other applications like data valuation, explainable AI. Again, each of these problems, there are many methods that are based on removal of one data point and seeing the impact of the removal of one data point on the prediction of the model. So in this talk, I'm just going to mainly focus on this hyperparameter tuning. It's a very classical problem, and I guess you can see why high dimensionality becomes important. And then towards the end of the talk, if time permits, I'm going to mention a couple of slides about some of our work in machine learning problem. Okay, so what is the hyperparameter tuning, and how is that the data removal problem appears here? This is the problem. Let's say we had this estimator beta hat, and in this particular case, as I said before, this is the regularizer that is controlling the variance of the estimator. If I let, for example, for most of the regularizers, if I let lambda go to infinity, beta hat becomes 0. And if lambda is equal to 0, usually the estimator has high variance. So the optimal choice of lambda, or this hyperparameter lambda, is of interest for most of the machine learning applications. And the question is, how do we want how do we want to find the optimal choice of lambda? This is the one of the methods that we have, right? So ideally, we want to find the choice of lambda that makes the prediction error smallest on new data points, right? So if you give me a new data point, x new and y new, from the same distribution, then I'm going to use beta hat based on the training data and see what is the prediction of beta hat on this new sample, and compare it with y new. If this prediction error is small, small, then we say that, okay, lambda is a good choice. But if this is very large, that lambda is not a good choice. So we want to kind of have access to this quantity. But unfortunately, in order to draw a new sample from this distribution, I should know beta star that we don't know. And I should have access to px, p of x that we don't know either. So there are so many techniques. This is a problem that has been studied for I guess from 1960, and it was a very hot problem until 2000, right? And there are so many techniques that have been proposed and are taught in machine learning courses these days. The most popular one in applications, I believe, is the cross-validation. But how does cross-validation work? Again, I'm focusing on a specific type of cross-validation that is related to removing one sample, but we can generalize it as well. The idea of cross-validation, or leave one out cross-validation, is that I'm going to just calculate beta hat minus I. So I remove the ith data point. I calculate beta hat here. And now, since the training data doesn't use xi, yi, this xi, yi becomes this new sample for me. So that's essentially the new sample. I don't need to have access to the distribution anymore because this is given and I know it's generated from the same sample. And then I calculate the prediction error. And we repeat this process. Since this is not if I do it for one I, this is not a good estimate. So I'm going to repeat it for different values of I and take the average. And this is called the leave one out cross-validation. So as you can see, this is, again, the data removal problem. So I have, let's say I originally calculated beta hat. I had access to that one. But now I have to calculate beta hat minus I when I remove data point I. And I have to repeat it for every single data point. So it makes it quite expensive calculation. And that's one of the reasons that maybe we don't like the leave one out cross-validation in the applications. So again, the approximate data removal problem is the following, right? Can I find an approximation of this that is computationally much more efficient, and still it's accurate enough? It's an accurate approximation of leave one out in high dimensional settings. So that's, again, the data removal problem in the risk estimation. And this is the first attempt for getting this approximation. And it goes back to Allen's paper and some analysis in Stone's paper. This is the proposal that Allen and Stone had back in the 70s. So the idea is that I have n data points, and let's say n is very large. I'm removing one data point. So the first assumption that Allen and Stone made in their papers was that, okay, beta hat minus I should be very close to beta hat, because out of n data points, one is removed. How much can that change the estimate? So I can start an algorithm, fast optimization algorithm like Newton method. And since I know beta hat is, and initialize it with beta hat, so I can use the Newton method, I initialize it with beta hat. And then I just do one step of Newton because I know these estimates are very close. So hopefully one step of Newton is going to be sufficient. So they suggested let's do one step of Newton and stop. Of course, there is the first assumption that everything should be twice differentiable because Newton method is like using Hessian. And if we do what Allen and Stone obtained eventually was this estimate, beta hat I is equal to beta hat. This is the Hessian inverse, and this is the gradient. So Hessian inverse gradient. And I hope that the notation doesn't confuse you. When I put L double dot, this is Newton's notation for second derivative. So I have just used Newton's notation for second derivative. So that's the Hessian essentially, Hessian of this leave one out problem. And this becomes like the gradient or minus the gradient, and this becomes the Newton estimate. So that was the first step. Instead of just repeating this optimization algorithm, what we are going to do is that I'm going to do it one step, stop the algorithm. But then they had this problem that wasn't, for each I, they had to calculate this Hessian matrix, which is a P by P matrix. And then they had to invert it. So still computationally, you have to do a bunch of inverses, matrix inverses. And you don't want to do that. It's too many matrix inverses. Potentially, it can be computationally expensive. So what Stone suggested in his analysis in 1977 was that, okay, you have this matrix is a bunch of rank one matrices. These are rank one matrices. We are adding them with each other. So this is n minus one. So if I add another rank one matrix here, it's not going to change things much. Again, we have n minus one rank one matrices that are added, n is very large. So hopefully if I add an extra rank one matrix, it's not going to change things by much. So Stone suggested that to reduce the computation even further, I'm going to add this term here. And this has this approximation has appeared in many of the recent application of the Newton method, especially in this Juan Leon paper that became quite popular. The same approximation appeared. And so there are two approximations. One is like doing Newton method once instead of just repeating it. And the second approximation is add a rank one matrix so that we just do the matrix inversion once and then be done with it. Okay, so the question is, are these approximations accurate? In low dimensional settings where P was fixed and N was very large, Stone in his paper showed that both approximations are fine and this is acceptable. Now we wanted to see if in high dimensional settings where we have lots of features, the approximations are still accurate. Let's start with the, yes, yes, please.
You could add any rank one matrix there. A lot of that particular one, like I have in the back of my mind data privacy issues. So why would people want to stay not there? Start with.
Oh, that's a great point. So regarding the privacy, I'm going to get back to the privacy later. In this, in here, you're not concerned with the privacy. So as long as the prediction is, as long as these two things are reasonably close to each other, we are going to be fine. The reason they add xi was that because every time I remove, we have to change I and calculate this for different i's. So if you add xi transpose, this j becomes j from 1 to n. So it is a fix. So that's the only reason. But regarding the privacy, we have to discuss more. You're right. As soon as we add that, we should be worried that maybe the residual information about xi is still there. So can the adversary detect that information? And that's a very valid point. No problem. Yes.
That's another question.
Yes, please.
So if you are basically adding like rank one perturbations to the matrix, why not just do a fast matrix update for the inverse?
Absolutely. That's what we're going to do. So I just
Okay.
wanted to mention that whether this what is done in this paper is correct or not. But if it's not correct, you're right. We have a very easy solution for it, and that's what we're doing. That's a great. Thank you. Okay, so this is some issue that happens in high dimensional settings, and this is one of the subtleties that every time we want to go from low dimensional to high dimensional, we have to be very careful about and make the analysis more complicated. So let's say I'm making the problem even easier now. And the problem is the following. I just, let's say xi is a Gaussian, independent Gaussian vector. And the elements of A are also IAD Gaussian, just a matrix, and then I'm calculating xi transpose A xi. So this is just a quantity. It's different from our previous problem, but as you will see, it's quite close. So it's very easy to see that some concentration, especially if the xi is p-dimensional and A is n times p, it's very easy to see that for large values of p, some concentration happens. And in fact, this quantity concentrates around this quantity. We can either use Chebyshev inequality to prove this one, or if you want to use something more interesting, Hansen-Wright inequality is going to give us this analysis. So essentially, this quantity is concentrating around trace of A transpose A, and that is OP and P. The order you'll see why it becomes important later. Now, let's do what Stone suggested. So I'm going to create another rank one matrix here, B, and add that rank one matrix. But here I'm assuming that V is independent of xi. And we do this. And if we calculate, so Stone said that if you add this rank one, doesn't matter. So you can still say that it's as if this one wasn't here. So if we calculate orders, this is a very easy calculation that we will get. So again, this is order NP. That's what we have in here. But then the second one, it's easy. It's a very nice, essentially theoretical stat one question that you can see that this is OPP. So it's a very small quantity. And since N and P are large, still this is much bigger than this one. So more or less this can be ignored, exactly as suggested by Stone. But here is the problem that happens in Stone's evaluation. If now the rank one perturbation that I add is related with xi, all of a sudden we see that this rank one perturbation can create p-squared error, and especially in proportional setting where n and p are at the same order, this rank one perturbation immediately create a very large amount of error that can potentially be even larger than this. So this is exactly what happens in high dimensional statistics. That as soon as you start having correlation between vectors, since you have too many of them, they add up and they can become very big. So you have to make sure that you're very careful about the correlations. So this is exactly the issue that happens in Stone's approximation. So if you look at it here, we added xi transpose, xi transpose, and the term that appears here is xi. So potentially this can cause an issue. And that actually, in one of the papers, we showed that this is actually creating a large error in the approximation and is not acceptable. So as you mentioned, this is not a big deal. So we can just revise what Stone suggested. still we say let's do one step of the Newton method. That's okay. But for the second step, we are going to do the matrix inversion level, and we calculate the exact inverse. So we don't need to use a stone approximation. The formula looks a little bit more complicated, but computationally it's not that different from the original proposal, so we can work with this. But the second step, there is no approximation anymore. But for the first step, we still are suggesting that we do one step and we stop. And the question is if this one step calculation is accurate enough and in high dimensional setting. Again, in low dimensional setting, the stones prove that one step should be sufficient. Okay, in high dimension, yes, please.
Just kind of a silly clarification question. It's actually not, I mean, there are regimes where P is growing with N, but it's growing slowly enough that the approximation will still be fine. So the question is, what is an acceptable threshold for the rest of growth, which I'm sure you guys have worked out in the paper. But so I guess one question you need to answer it now is, in practice, how do you distinguish problems where the rate of growth is expected to be large enough that the approximation will still work, and what other problems you do really need?
That's a great point. That's actually one of the directions that we are currently working about. In general, there is this high dimensional asymptotic that we consider proportional asymptotic. They're growing together. And then there are these other asymptotics that P is growing more slowly. Exactly. So now the question is, okay, we have like a practical problem with a given P and a given N. Which of these asymptotics are a better match to this finite problem? And one solution that we are currently exploring, which seems to provide some good information, is that if we just go with the current asymptotic framework, it's very hard to answer this question. However, we are kind of back to the problem that, let's say, Edgeworth was concerned about central limit theorem. Everything seems to have satisfied CLT, all the distribution, but then for finite samples, some of them are closer to Gaussian, some of them are farther apart. Then he started saying that, okay, maybe first order expansion is not good enough. I have to go higher and higher order. So we tried to develop like higher order asymptotic for these types of problems and some other high dimensional problems. And what's something that we notice is quite interesting. For many problems, when you go with these other asymptotics, the second order all of a sudden becomes very close to the first order. So those asymptotics are not acceptable for the particular PNN. You plug it in, the second order is close. This is not good. In here, so far, we see that the first order is like constant. We are not in consistency regime. And in these problems, the second order is like square root n. So as long as n and p are large and p over n is not too small, they seem to be accurate. But that's an ongoing work. So we're still thinking about it. That's a great question. Okay, so this is the first result that we managed to prove a few years ago. Essentially, okay, we have assumed that the features of Gaussians with some covariance matrix. The covariance matrix is just well conditioned. It doesn't have zero eigenvalues. And then, as I mentioned before, n over p is a constant. So delta is just a constant. That's the asymptotic we are considering. And then what we can show is that if we do one step of Newton, the difference between leave one out and a low is some polylogarithmic term divided by square root n. So it's small. And one thing that is even more interesting is that the error between leave one out and out of sample prediction error is 1 over square root n itself. So doing more than 1 Newton step is not even worth, because essentially the prediction, the accuracy of LO, leave one out itself, is 1 over square root. So this is the more or less the best we can get, and the one step of Newton is offering that error. I'm not going to talk about the proof of this one. I'm going to mention another result later, and you will see some of the ideas in the proof of this one as well. Yes.
Just in some ways, harking back to the previous question. So you have the variance of the X depending on n, which
Mhm.
means that the more observations you have, the less your X variance.
That's
So you could, I imagine, potentially rewrite that in terms of something where the sigma doesn't change, but instead of working with the ratio of n to p being constant, it would be something like n squared to p or something like that being
Exactly.
constant. Wouldn't that be
So that's a great one. So how do we, that's a great question. So in these asymptotics, there's so many things that are playing.
Correct.
working.
And it's just that for me, it's easier to understand keeping the variance fixed and thinking about the rate of growth of p with n,
Exactly.
as opposed to thinking it this way.
So the way we are thinking about this problem is that, and the scaling is working here. Since p is growing, we have like a long feature that is multiplied with this. And then beta i's, you're assuming that are order 1. So we are trying to make sure that the signal to noise ratio per observation is remaining fixed. So that's where the scaling is coming from. So the measurements, it's not that as you grow the dimension, the signal, you're also increasing the signal to noise ratio per observation. So that's why we are, this is kind of the sweetest spot to make sure that you are not going to get exact consistency. It's not that the best risk you can get is going to go to 0. It's going to be a constant thing, and then you're trying to approximate that constant function. But again, as soon as you change it, you go to consistency regime, and those issues are going to happen. That is the second order term now close to the first order or not. And that's something we are thinking actually more these days. No problem. Yes, please.
I just want to ask, this theorem is for union for variances for all i's, or is this
Oh, that's a great point. Yes, the probabilities that we have, this is for one of them. The probability I haven't written like this is very vague here, high probability, but that's an exponential thing. So even if you do it in all the data points, it's going to be individually, it's also correct. We are not using the fact that this is a sum of sum over I, and it's just true for that one. Even if you look at the individual terms, they have the kind of a similar guarantee. No problem. And then if you're also interested in the uniformness over lambda, that hyperparameter, as long as this hyperparameter is like finite dimensional, it's easy to extend kind of Wald's argument for uniform convergence and get the uniform convergence. It's just that then you have to be careful about probabilities. The probabilities, you will get OP of this thing, but you can't calculate the probability exactly. If you don't care about that thing, you can easily extend it and make it uniform over hyperparameters. No problem. Okay. So like the first extension that we were thinking about is, of course, back in the 70s, people were not particularly interested in non-differentiable things. High dimensional features wasn't a thing. So most of the things were differentiable. That's why Stone essentially suggested the Newton method. But for high dimensional settings, we have a bunch of reasons to use non-differentiable stuff. These are some of the standard regularizers that we have, and then also some of the loss functions are non-differentiable. And the question is, okay, what should we do now? Can we still do data removal very efficiently and accurately in high dimensional settings? And again, for the sake of clarity of this talk, I'm going to focus on the lasso, which is the easiest one. And it's easier to explain what is happening and what are the challenges. But the framework can be extended to some of the others, not all of them, but some of the others as well, including group lasso and look near law. Okay. So this is the lasso problem, very simple one in linear regression. So we have the quadratic loss and L1 regularizer. And now we want to solve the leave one out estimate. So what should we do? The first quantity that we define is like SAT, which is the support of beta hat, meaning that these are the locations. So one thing, if you don't know what the L1 norm is, it's the sum of absolute values. So at the 0, it has a kink. So it's not differentiable at 0. The regularizer is not differentiable at 0. But also many of the beta hat i's, they are actually zeros. So that kink point is very important when you want to do the calculations. So how should we then approximate? The idea is the following, right? Suppose that I define S hat as support of beta hat, locations that beta hat is not equal to 0. So they are not 0. And then let's say S hat I is the support of beta hat mine. Again, the location or the indices of the elements of beta hat minus I that are not 0. So they are these 2 quantities. Now, we can make this assumption that, and the assumption is that, again, we are just removing one data point. So hopefully, if I remove one data point, it doesn't change the support of the solution. So in every place that beta hat is not 0, beta hat minus I is not 0 either. If I accept this assumption, then we are back in business. Everything becomes quite easy, because then I'm going to change my problem. I say that, okay, I know where the zeros of beta are, beta hat minus I are. I don't care about them. I'm going to set them to 0. And on the other locations, I'm going to solve this optimization problem now. So I just remove the zeros, all the zeros, I set them to 0. For the other ones that are non-zero, I'm going to solve the optimization problem. As once I solve the optimization problem, we know that all of these things are non-zero, so they are not at the kinks. And this is a differentiable function. So I can easily do the Newton method like before and apply, get a nice solution. So this is just a formula. I just want to say that the formula becomes very nice. So we get an ALO formula. But again, I want to emphasize that I have made this assumption that the active set, the support set, doesn't change as if I remove one data point. Okay, so there are 2 questions. Yes.
But the solution to that could then lead to some of the ones that were not 0 before to now being 0. So that's not quite.
That's not quite there. Absolutely, absolutely. So the assumption more clearly is that if it was both of them, like non-zeros, have to become exactly the same. And even when you solve this optimization, everything that's non-zero remains non-zero. So there is more assumption. Actually, that's correct. So the first question is this assumption correct? And the answer, unfortunately, is no. So this is a simulation that we did that was a little bit surprising. So we are doing lasso, and this is the histogram of the number of changes in the support. So what does it mean? Let's say we did all the leave one out problems here. So how many of them are there? 500 leave one out problems. And then over these 500 solutions, I checked how many have the same active set, have the same support as the original problem. Around 70 of them had the same support, but then around 50 something of them, the support was different by 1. And some of them like more, as you can see. And some of the leave one outs, their support set was different in around 49 locations than the one that compared to the original one. So unfortunately, it seems that even if when we are in high dimension, as soon as you remove one element, the support changes, and the change can be dramatic. So that's the difficulty of the problem. But here was the interesting or surprising result that we got. So we then said, okay, these errors are happening, but let's calculate the risk as a function of lambda. So the orange here is the leave one out, as a function of lambda, the hyperparameter of lasso. And the crosses are the approximately one out, as you can see. So they match quite well, even though the active set is changing. And my formula was based on that assumption, but still the formula itself working, even though the assumption is violated. And there are some issues here. I guess now we understand why this is happening, but in general, the approximation is not bad, even on very hard lasso type problems. Okay, so we wanted to understand what is happening here, and we proved eventually something, and I'm going to explain where it comes from. Unfortunately, this is not as strong as we want it to be. It's a weak theorem, but at least it shows that the approximation should work to some extent. So we essentially, this is, let's say, you're using the elastic net or the lasso problem, and we have some smoothness assumptions on the loss function still. And what we could show is that the formula that we got, the difference between A low and leave one out is now some logarithmic factor over n to the power of 1/12. Again, I would like to say that in the smooth case, we had 1/√n, which was kind of the optimal which we should shoot for. And here it's much worse than that. So I don't think this is necessarily a sharp result. But we couldn't find a way to improve. We haven't been able to find a way to improve it yet. So, but what is happening, essentially what this result is saying is that, yes, the active set is changing, but there are two things. The active set is not changing, the support is changing, but the change in the support is not too large. That's the point number one. And the second thing that it proves is that when it changes, the error that each change is introducing to the estimate is not large either. So you can still control the error between A low and leave one out if you just make that assumption that the support set is not changing. I can mention that a little bit about the proof. I'm not sure how much time I have. I can go to the proof.
10 minutes.
10 minutes. Okay. So let me mention a little bit about machine learning. And then if I have 2 more minutes, I'm going to go back to the proof and tell you about some of the ideas of the proof that are okay. So let me tell you a little bit about machine learning. What is the machine learning? As I mentioned before, the idea is that we want to remove the influence of specific data points on the trained model. And the main reason is privacy regulations, right? So I guess the GDPR, the right to be forgotten, is from Europe, but California has another one. I forgot the name of that regulation. Because of these things, they have to, first of all, remove sensitive or incorrect data if the request comes, let's say, from the government. And also, they have to, if a user asks them to remove the data, they have to remove it from their models as well. So what are the key challenges here? Of course, the first one is computational efficiency. As before, we want it to be very efficient. Of course, we want to maintain model performance similar to what we had before. We don't want to get a model that has nothing to do with this model. We want to have the accuracy. But in addition, we have the third requirement on these models that if you do it approximately, some residual information about xi, yi is still in your model, and the adversary can prompt your model so many times and essentially detect that information. So what can you do to make sure that you're not violating the privacy just because of your approximation? And this becomes related to many of the things that appeared in the privacy literature, including differential privacy. So there are so many notation. I'm going to try to clarify the notation. The idea is that, let's say, this is my approximate algorithm based on Newton method, for instance. I know that there is a residual information because this is approximation about user I. because this is an approximation. So what we do, let's say we can add some noise to it to hide that residual information. We are hoping that the residual information is very little. So if I add a little bit of noise, then I can make sure that I hide that information. But how can I make sure that we have hidden that information? The idea is that we look at the exact, let's say, leave one out problem. So that's the exact leave one out. And I add the same amount of noise. And I say, if I look at the likelihood ratio of these two things, and the likelihoods are very similar, if the ratio is 1, then the user cannot, the adversary cannot detect any information, because this is as if you have the exact data removal plus noise. But then we consider some margin. So we say 1 is the ideal. I'm going to make it e to the power of epsilon, just give it a margin to make the problem a little bit easier. So this is the epsilon, more very related to epsilon differential privacy. And the question is, can we do this thing by using these approximate methods? One thing that we managed to prove in a paper was that now this time, if I do just 1 step of Newton, it's not going to work. The amount of noise, even for removing 1 data point, if I just do 1 step of Newton, it's not going to work, because I have to add noise, and this noise is so large to hide the residual information that my predictions are not going to be good anymore. However, if I start doing 2 Newton steps, at least the predictions are going to start becoming more reliable. So as soon as we add like this privacy constraint, we need to do more computation. Now, of course, the more important question is, what is the trade-off between privacy constraint and computation? That's a bigger problem that we are hoping to answer later. Now, do I have like a few more minutes or no? I'm done.
5 minutes.
Oh, great. So now I can tell you a little bit. I'm sorry, I'm done with machine learning. I'm going to tell you a little bit about the proof. There are some interesting things about it that I guess it's going to help understand what's happening. So the first idea, as I said, if I want to show in the non-differentiable case, in the lasso case, we have a good estimate is that the support set is not changing much. That's the first step. So if you do some analysis, eventually we will be able to show that the difference between the original estimate on all data points and beta hat minus I that doesn't have access to the ith data point. If I calculate the L infinity norm, let's forget about the polylogarithmic factor. It's like OP1 over square root n. So what can we say if beta hat, let's say J, index J of beta hat, is non-zero and it's not in the 1 over square root vicinity of 0, it cannot become 0. So those that are very far from 0, if I change 1 data point, if I remove 1 data point, they remain non-zero. So I have first to count, if I want to see which points are going to fall, may fall on 0, I have to count how many of beta hat J's are in the vicinity of 0, 1 over square root n vicinity of 0. So let's say we count them. I intuitively and heuristically of my calculation show that they should be square root p. But unfortunately, we couldn't show that. We have shown n to the power of 1 over 5 over 6. That's why that our errors are not great. Now, this is the first step. But then what about 0? So if a coefficient is 0, even if I change them by 1 over square root n, they're going to jump out of the act. They're going to become, they are going to come into the support. So I have to also control those things. Apparently, this method doesn't work on zeros. So then we go to the subgradients and try to prove something similar to this one on subgradient, and then count the number of elements that give us certain values of the subgroup. Eventually, everything boils down to counting how many of the beta hat J's are in the vicinity of 1 over square root n, and how many of the subgradients are in the vicinity of 1 and minus 1. So we have to count them. And the way we do the countings so far, which again, this is, I guess, it could be another reason our results are not sure. is the Gaussian minimax approach that helps us calculate some of these. So that's where our theorem came from that has unfortunately this error. So this is the proof for this result. Okay, so I'm done with my talk. So there are so many open problems. Of course, sharper results for non-differentiable cases. One of my colleagues emailed me yesterday and said he found a new way to prove the non-differentiable cases. I haven't read his paper yet, but I'm hoping that that may help us make these things sharper. Other applications, data attribution, data valuation, they all have their own constraints and issues. More complex models, neural networks, I'm going to mention one more line about it, and then further reduction of complexity and memory usage, of course, is another interesting thing. And in the last paper here that I didn't talk about, we tried to extend the results to neural networks to some extent. So thank you so much.
Any additional questions? One.
Yes.
So for the non-differential case of the lasso, I don't know what your colleague has written down, but have
Me
you
neither.
tried playing with like semi-smooth using type methods on the proximal gradient method?
We have, so even in our proof, like some of the things that we have proved here are based on smoothing the lasso and then trying to see what happens when I change the smoothness. But even there, we have this issue about the level of the smoothness. And,
Right. But what if you look directly at the optimality condition and try to run a non-smooth type method? So for lasso, you have there's like very specific things happening, so it actually converges.
I see. I have to think more about it. So you're suggesting that I just
So there's an algorithm that basically goes from the penalty formulation to the fixed point equation, which
Mhm.
says the proximal gradient as a fixed point.
exactly.
And then you put that in a norm, and you
Uh-huh.
minimize the norm with the non-smoothing. So basically what you do is you look at limits of Jacobians.
I see. I see.
So there's some theory by Defonson that
Uh-huh.
says this thing should converge
I see.
for polyhedral regularizers, and I think for the Gaussian stuff.
Okay. Okay, I have to